We have just defined and quantified the upper limit of maximum performance for any system operating in a cycle. I'd like to walk you through sort of what I would illustrate as a real world example of the power that you now have as an engineer to analyze some things that people might offer to you, and you can give some very quantitative, well thought out, well reasoned, and hopefully well explained reasons why you believe that the proposal is possible or impossible. So this video does have to do with being able to quantify if something that's proposed to you is possible or impossible. In other words, a system operating in a cycle. Is that proposed cycle, is it possible or impossible? And so that kind of question is commonly asked throughout nearly all of society in various forms of questions or statements. Here's a hint. Snoopy has another hint for you. This is also a commonly asked question on quizzes, tests, and the exam. Is the following situation possible or impossible? And you're asked to quantify and explain. So this can have some value to you. Let's look at some other forms of this question that I've encountered throughout my practicing career, socializing with people, just in my everyday life. So here's a commonly asked question. Why can't power plants be a lot more efficient? Because, they understand I'm an engineer and I should be able to answer that question. Sort of fussing at me for power plants not being more efficient than they really are. In fact, there are some demonstrative people that will say, why can't power plants be 100% efficient? Things just aren't right. We've got a lot of energy situations going on here, and we're concerned about our planet. I fully understand that. So we think power plants should be able to be 100% efficient. Another question. Why does it take so much electric power to run my air conditioner? Why is my electric bill so much higher in the summertime than it is in the wintertime? Another commonly asked question, what's the best gas mileage that I can expect from my car? Another commonly asked question for folks that do own or operate heat pumps in the wintertime, say they observe, why do heat pumps operate so terribly on very cold winter days when that's when we need a heat pump the most, on a cold winter day? Why is that? And you're going to be able to answer that as well. So let's get moving on some example problems. Oh, you're going to be able to answer all these questions very effectively and respectfully when you finish this course. Okay, so I need to get you set up for something that might not be so clearly made in the book, and even sometimes in class. Classes we operate at a breakneck pace. We have so much material to cover. There might be something a little subtle here that I'd like to fill in some blanks now that I've got the video time to sort of explain this. So here I'm showing two systems operating in a cycle. One's a power cycle, one's a refrigeration cycle. And the question is a proposed system operating in a cycle between two heat reservoirs, TH and TL, is it possible or impossible? Let's go through some logic so that you can provide a well thought out and respectful answer, and you can quantify this now. So here we go. So if we think about this, so the answer might be, well, the process is possible. So if the process is shown to be possible, you have to keep your thinking going. And there's another question then. Is the proposal possible and reversible, or is it possible and is there something irreversible going on within that black box cycle that you can't see, but at least you can tell there's something going on that's irreversible? So do you get it? So if you determine that a proposal is possible, you have to take one more step and determine, is it possible and reversible, or is it possible and irreversible? Now, on the other side, on the right-hand side, if you determine that the proposed process or cycle is impossible, boom, you're done. You're done. You don't have to figure out if it's reversible or irreversible or anything like that. It's impossible. It would violate the second law of thermodynamics. And so this is sort of the thinking you have to go through, and this would be a complete answer. When you find a cycle is possible, you need to follow up by saying it's possible and reversible, or it's possible and irreversible. I'm going to try to step you through this by way of examples. Okay, you're a practicing engineer, okay, and you're working for a company, or maybe you're running your own company, and you're interested in installing a new power plant. And a salesman comes to you. So here's a picture of a salesman down below, very nicely dressed salesperson, and he is trying to sell you a system operating in a socket. He's trying to sell you a power plant, and he says he has designed a power plant, this guy, and he's trying to sell this to you, a power plant that produces 800 megawatts of net power, and it requires 1,200 megawatts of heat transfer to be delivered from the high temperature reservoir. He says further, his reservoir is at 727 degrees C, and he says, I'm going to reject heat at 27 degrees C. That's typical for the surroundings, okay? And then he says, okay, he's trying to sell you this. When can we start building it with your money? Can you write me a check? We're ready to start building this thing with your money. What do you think? So here's your job. Determine if the proposed power plant is possible or impossible in the first place. Is this person trying to sell you a bill of goods? Or at least is the proposed process cycle possible? I said possible even. All right. I'm going to try to give you a recipe on where you'd go from here. Okay, so there's the question repeated. You're going to start with a sketch. You'll draw that power cycle schematic, and you'll scratch down the given information on that schematic. That's common sense. The next thing you're going to do is you've got enough information to determine the claimed thermal efficiency. That's easy. Energy sought over the energy that costs. The next thing you're going to do is determine the maximum possible thermal efficiency and compare those results. Now, I got a little confused on my slides, and so I needed to add a bullet item in my slide, and I didn't add it up higher. Sorry about that. So let's back up a little bit. We determined the claimed thermal efficiency. The next thing I do is I convert my temperatures that I've scratched out on my sketch to absolute temperatures. I do that first, right? Then I determine the maximum possible thermal efficiency. Okay, now I've got two thermal efficiency values, two numbers that I can compare. And then I'm going to use Common Sense 101 to make my conclusion. Once I've got two numbers to compare in terms of efficiency, I can make these decisions. Is it possible and irreversible? Is it possible and reversible? Or is the salesman's proposal impossible? So let's look at the solution. Here's my sketch. I have written down the given information, 1,200 megawatts and 800 megawatts. And darn it, it looks like I did not label 727 degrees C up here and 27 degrees C down here. Shame on me, I didn't complete my sketch, okay? But I have written down my governing equations over here. At least I've done that. So the claim to thermal efficiency is the energy sought over the energy that costs. Wow, just by inspection, that's going to be 800 over 1,200, isn't it? Energy sought 800, energy that costs 1,200. I've done that down here in Excel to determine the claimed thermal efficiency is 66.7%. That's what my salesman's claiming. Now I'm going to check the maximum possible thermal efficiency. I'm going to go to this fundamental and say, wow, I've got TH minus TL over TH from that derivation. I've got my temperature. So what I'm going to do, first thing I'll do is convert 727C into 1,000 degrees K and TL to 27 degrees C into 300 degrees K. I turn the crank on my calculator and I see that the maximum possible thermal efficiency is 70%. And so I can report back to the salesman that I might not be ready to start building this power plant. However, the proposed plant is possible and it is irreversible because the claimed thermal efficiency is less than the maximum possible thermal efficiency. This is a powerful tool when you're working with salespeople, when you're working with coworkers who you're working together in energy energy transformation problems, energy transformation projects. So I hope you see it. You'll have to excuse sort of my blunder of not completing my sketch properly, and also my little bullet item of leaving out. We got to switch to absolute temperatures first. Now, another salesman shows up. He either overheard us talking or he's also trying to bid on this particular proposal. I'm seeking to build a new power plant. And this different salesman comes in and says, I can do a lot better than that first proposal. So you need to buy this from me. I've designed a power plant that produces 1,000 megawatts of net power and requires that same 1,200 megawatts of heat transfer at 727 degrees C, and we're rejecting heat at 27 degrees C. So when can we get started building this proposal with your money? Don't go with that first salesman. You got to, I'm good. I'm good. And I'm going to give you a lot more bang for your buck with this much higher efficiency. Let's test this person's proposal. And I did a copy and paste, didn't I? And I still didn't label my temperatures on my sketch. But let's see. Let's do energy sought over the energy that costs for our new sketch, new proposal. Let's see, 1,000 over 1,200. That's 83.33% claimed thermal efficiency from the new salesman. Now, I dust off the work that I previously did from my first salesman, and I don't need to repeat it, do I? I just discovered, of course, that the maximum possible thermal efficiency for this similar situation is 70%. Okay, wow. Maximum possible, 70%. Salesman claimed 83.3. All I got to do is shake my head and I say, well, salesman number two, shame on you. You're trying to sell me something that's just flat impossible. It's impossible. So I will respectfully dismiss you from my office. Thank you for coming in, but I'm afraid your claim is impossible. Okay, that's it. So you're not going to get burned wasting your money. That same salesman comes back in a few weeks and he says, okay, you caught me. I need to adjust my claim. Okay. I've designed a new power plant. My new power plant that I'm trying to sell you produces 840 megawatts of net power. It requires that same 1,200 megawatts of heat transfer from 727 degrees C, and I'm going to reject heat to that same surroundings at 27 degrees C. Now, when can we get started building this new plant with your money? So I'm going to go back and it should go pretty fast, shouldn't it? Because I've got something in Excel. I can dust off my previous work and test the new claim. My same incomplete sketch where I didn't label my temperatures, but let's see. The new claim is 840 energy sought over 1,200 energy that costs. So the claimed thermal efficiency is 70%. Okay. Wow. I dust off the previous work since my numbers corresponded to see that the maximum possible thermal efficiency is 70%. Huh? Wow, that sounds familiar. These two exactly match. So my salesman, so what he is trying to sell me is a power plant that is possible, and on top of that, it's reversible. Okay, so of course, a little team of us would need to really, we would have to dissect what's going on in this black box. But certainly from our computational standpoint, the proposed plant is possible and it is reversible because the two measures of thermal efficiency match each other exactly. And so that's an expression of a reversible cycle. That makes sense? So you get the idea. So that's my claim is you get the idea that now that you've got an analytical skill now in mechanical engineering that you can put to use. Okay, it's got to be a system operating in a cycle. Of course, you need to be pretty good at your cycle schematic. Uh, Typically, you're given 2 out of 3 of the cycle schematic energy transfer values. Typically, you've got 2 out of these 3. So you can get the third because you're good at the first law. Okay. Uh, then you determine the claimed performance measure simply by energy sought over the energy that cost, depending on the cycle. Okay. Then you have to either be given or figure out the high and low temperature reservoir temperatures. Either you have to be given them or somehow through some engineering practice understand what's the value of TH, what's the value of TL. You must be able to get that, and that's going to enable you to determine the maximum possible performance. You're going to compare those two values, use Common Sense 101 to determine your conclusion. This is a classic quiz question, classic test question. So we've reached our recap of is it possible or impossible? I hope I've illustrated with numbers how you would do this type of analysis. Remember that if your analysis reveals that it's possible, you got to take one last step and determine is the proposed plant possible and reversible, or is it possible and irreversible? Okay. And then if you've determined that the proposal is impossible, you're done. It's impossible. So I hope that helps. Now, on the short term, uh, that little review is going to help you on quizzes and at least one of your tests, and probably an exam question, because this is a common occurrence for practicing engineers who are involved in energy transfer, thermal, fluid, heat transfer systems, and production of power and or heat pumps and refrigeration systems. Okay, hope that helps. And join me next time for more quantifying properties associated with the second law of thermodynamics.